otherwise. So key things to note that were in these notes is that test number 2 is on Tuesday, November 17th. Okay. So what I'll do is I'll copy this over here, copy, just do it right away. Oops. So what we were saying was we're gonna have tests on November 17th, on the Tuesday. We won't have time to do a review day because we're kind of cutting it close. And then I want to do a mini test at the very end of the term so that you've seen all the material on a test before the final exam. Then we talked about, okay, so let me copy this. Copy. We finished inverses, and then we talked about quadratic functions. The hard part is putting it into standard form. So from general form, a quadratic into standard form, but we'll practice that again, completing the square. Oops. And then that's not for us. So then here, here are the problems we were asked to do. And just as a reminder, I'm going to copy in completing the square so that we have it for reference. There. All right. So at the end of last day, I asked you to try 23 on your own, and then we would go through and we would use it as review. So here we go. 23. First thing we have to do is express this function, this quadratic function, in standard form. That's the hardest part. Once we have the standard form, it's easy to find the vertex as well as the x and y intercepts. You don't need standard form for that, but I think it's easier. Then we can sketch a graph, and then we can find the domain and range. And then what we'll do is we'll check all our work using Desmos. So f of x is negative 4x squared minus 12x plus 1. What I have to do is I have to use completing the square in order to write this in standard form. What's hard is x squared plus bx is what we're working with, so we can only have x squared plus bx, which means we can't have this negative 4. I have to factor out that negative 4 first. And so what this looks like is factor out negative 4. Okay. Another thing that we see here is negative 4x squared. Well, this negative 4, just looking at it as ax squared plus bx plus c, well, this is a negative a, which means this thing is going to be pointing down. So I want to make a note of that too. Since a is negative 4, which is less than 0, oops, move it up, that's all I wanted. The parabola is facing down. The parabola is facing down, okay, which means it's going to look something like this. So the vertex is going to be a maximum. Oops. Vertex will be a maximum. Okay, so there are a lot of things that we know just from this negative 4. So whatever a is tells us a lot. Tells us this parabola, we're expecting it to go downwards, and because it's negative, and therefore the vertex is going to be a maximum. Okay, so if we factor out a -4, if we're looking for something in the shape of x squared plus bx, I can factor out a -4 from here, this term and this term. In fact, that's what I have to do. So I get -4 times x squared. -12 factoring out -4 puts me at plus 3x. And then what I can do is I can add the +1 outside. That way I don't have to factor out a -4 from all of it. I can just leave it as +1. Okay, so now I have to make a perfect square out of this by completing the square. Make this a perfect square by completing the square. Okay, completing the square says that if I have something like x squared plus 3x, I have to add b over 2 squared, and I know that seems weird, but it works. Okay, so x squared plus bx plus b over 2 squared, I can rewrite as x plus b over 2 all squared. But if I'm adding b over 2 squared, I also have to subtract b over 2 squared. Right? So that's what makes it hard, because otherwise I'm altering the meaning of this thing. -4 times x squared plus 3x, and I'm going to make a note here that b is equal to 3, positive 3. So then plus 3 over 2 squared. Okay, so now I'm doing plus b over 2 squared, but then I also have to subtract minus b over 2 squared. Don't forget about that +1 on the end. Okay, so here, now I'm adding 0, right? If this is a number and I'm subtracting the same number, right, they are, I'm technically adding 0. So I'm not altering this thing. I'm just making it work to my advantage. Because now what I can do is I can group this into a perfect square, remembering that this -4 has to get brought inside, right? So if I'm breaking off this piece and putting it outside the brackets, then I need to bring this -4 inside first, okay? So this here makes a perfect square. Okay. One thing that we need to remember is that this -4 has to get multiplied over here. So what this looks like is I get -4 times x plus 3 over 2, oopsies, squared, right? Going from here, I have this, I can rewrite it as x plus b over 2 all squared, so perfect square. So I've rewritten this as x plus 3 over 2 all squared. Then I've got minus -4 times 3 over 2 squared plus 1. Okay. Right, I had to bring this -4 over here as well when I multiply it out. All right, so now I can simplify this thing. I can bring the square inside. The square, remember exponent laws say it becomes 3 squared over 2 squared. 3 squared is 9, 2 squared is 4. So what this becomes is we get -4 times x plus 3 over 2 all squared plus 4 times 9 over 4 plus 1, but 4 over 4 is going to go away, so in the end I have plus 9 plus 1, so plus 10. So this becomes negative 4 times x plus 3 over 2 squared plus 10. Here, this is in standard form. If we compare it to standard form, maybe what I'll do is I'll just kind of move this up here. Standard form looks like a times x minus h squared plus k. Okay, so in this case, a is negative 4, that's the same as before. H, I don't know why I wrote it on an angle. It's just kind of like a side note, but here I'm just gonna see if I can I'll rewrite this out. ax minus h squared plus k. So a is negative 4, I'll write that up here. Therefore, a is negative 4. H has to be minus h, so h must be negative 3 over 2. And k is 10. Okay. So here, now that we have the standard form, we can use that. In fact, we don't really need these brackets here anymore. So just to simplify things, I'm just going to delete them. You can keep them, they're not doing anything. So here we are in standard form. Part B of these questions wants us to, so A is definitely the hardest part. Part B, you have to find the vertex and the x and the y-intercepts of this thing. So the vertex is at hk, which in our case is at negative 3 over 2, 10. Okay. Just to check in, negative 3 over 2 is negative 1.5. So in terms of our graph, just to get an idea of what's going on here, x is negative 1.5 and y is 10. So somewhere up here, negative 1.5, 10. So I'm expecting, because I know my a is negative, so I'm pointing down just like we said. So we expect to see here. We are expecting to find x-intercepts. There was one time that we did this where the vertex was down here, let's say, and it was pointing down. In that case, we don't expect to see or to find any x-intercepts, right? So this is just a check-in point. Am I expecting to find x-intercepts? X-intercepts are where it crosses the x-axis, right? So we're expecting to find x-intercepts, right, which is where y equals 0. Okay. So here we said where y is 0, that's our x-intercept. So let's make a note here. The x-intercepts where y is 0. Because we worked hard for the standard form, let's just use it. You could use the quadratic equation if you wanted to, use the general form up above. You'll find the same answers, so it doesn't really matter. So f of x is negative 4 times x plus 3 over 2 squared plus 10. So if we're forcing y, which is equal to f of x, to be 0, 0 is negative 4 times x plus 3 over 2 squared plus 10. Oops. So now, if I have to solve for the values of x that make this 0, I know I'm going to find two values, right? And what that's going to come from is this square. Okay, so we'll just keep solving for x here. So minus 10 from both sides is negative 4, x plus 3 over 2 squared. Divide both sides by negative 4, move it over here. So you get negative 10 over negative 4 is x plus 3 over 2 squared. Negative 10 over negative 4 is positive 10 over 4. I'm not going to simplify it. You can, but nah. I'm going to take the square root of both sides in the same breath, remembering that when we take the square root, we actually get the positive and the negative result. So this becomes plus minus square root of 10 over 4, which is x plus 3 over 2. Solving for x, I have to subtract 3 over 2 from this thing. Notice that this is all in the square root, the plus minus, and then I'm subtracting 3 over 2. So I get x is plus minus the root of 10 over 4, then minus 3 over 2. We can simplify this, we can write it, because we can split the square root up, root 10 over root 4. Root 4 is 2. We've got a common denominator. I'm going to leave it like it is, though. So this is the exact form. But in terms of graphing or sketching, the approximate form is going to be easier. So what I'm going to do is I'm going to find the decimal approximations of this thing. So I'm going to do the positive root 10 over 4 minus 3 over 2 first. So I get the root of 10 divided by 4 minus 3 divided by 2. Oops, not 29, there. Puts me at roughly 0.08113888. And if I do the negative version of root 10 over 4, 10 over 4, oops, 10 divided by 4, square root that, minus, I don't think I did the negative square root of 10 divided by 4. Okay, here we go. Minus 3 divided by 2 in brackets. I get x is roughly negative 3.08113888. Roughly. This will be a lot easier to deal with, right? These decimal approximations when we're sketching our graph, which is one of the things we have to do. So it looks like, right, our graph is kind of coming together. Looks like it's going to be shifted over a little bit because one of them is positive and the other one's negative, right? Which means we're going to have a y-intercept. So the y-intercept is, so where we're at now is at negative 1.5, 10. And then we said here at 0.08118, oh, sorry. How about we just stop there? 0. And then here maybe at negative 3.080, right? It's going to have this kind of curved form. And so now we can sketch it already. Oops, that wasn't very good. Something like that. The y-intercept is where x is equal to 0, right? So we have to solve for y where x is 0. And it looks like we're expecting to have a y-intercept. We'll always have a y-intercept. So here we go. Where x is equal to 0. So again, we're going to have f of x, and I'm going to use the standard form because we worked hard to find it. -4 times x plus 3 over 2 squared plus 10. Plugging in x equals 0 here, I get negative, so f of 0, the y-intercept is f of 0. -4 times 0 plus 3 over 2 squared plus 10. So I get -4 times 3 over 2 squared. 3 over 2 squared is 9 over 4. So I get -4 times 9 over 4 plus 10. Of course, this -4 and 4 are going to cancel to make -1. So I get -9 plus 10, which is just 1. So this, actually, the y-intercept, actually, that's spanning 2 pages. That's not very good, is it? Copy this guy down here. How about that? So now, this thing is at 0, 1, right, from here. This is also what we were asked to do in part C, sketch the graph. So this is our sketch. From here, we can find the domain and range. And then the last thing I'm going to do is I'm just going to check my work using Desmos. So here, C, sketch the graph. Okay, we kind of did it as we went along. It's not a very nice sketch, but things, all the things are there, right? We've got our x-intercepts, our y-intercept, our vertex. We've got the shape going down, just like we expected it to. And from here, right, we can find the domain is all real numbers. As a rule, the quadratics are always going to have a domain of all real numbers. So from -infinity to +infinity. And then the range is just looking at the y values, right? So it looks like the range, it's going to go from -infinity up to and including 10, right? So it always includes the vertex, whether it's the maximum or the minimum. So D, the domain, is from -infinity to +infinity, and the range we said was from -infinity up to 10 and including 10. You want to confirm this using Desmos, right? And so you want to make sure that all the things you found here are the same that you found in Desmos. So confirm your work. Always confirm your work using Desmos. So what you should do is graph the original function, right, in general form, graph the standard form, make sure you get the same graph, otherwise something happened, right? And then check your vertex and your intercepts and just the overall shape to make sure that it looks like the sketch that you made. So I think I might still have it here in Desmos. Let's see. It's thinking. Nope, got rid of it. That's okay. We'll flip back and see. The general form was -4x squared minus 12x plus 1. Okay, we can cheat and we can just kind of have a look at, okay, so the vertex looks the same as what we found, so that's a good thing. All the intercepts look the same, so we're on the right track, right? So that's very exciting. And just to confirm that we get the same graph when we do the general, or sorry, the standard form, -4 times x plus 3 divided by 2. When you do that x plus 3 over 2, you want to make sure that your x isn't also being divided by 2. And then step that out and finish the brackets to the power of 2 plus 10. All of a sudden, looks like we have the same graph. So we're all good. And of course, we can check our vertex and our intercepts again. Nice. So to finish off 3.1, we've actually already talked about, oops, here. So definitely work through these problems where you have to graph these functions. This is the takeaway message from this section. We can also talk about maximum and minimum values, but remember that's just the vertex, right? And so we can talk about the maximum or the minimum value as soon as you found the vertex HK using the standard form. Depending on which way it's facing, we already talked about the maximum and minimums. If, this is a big if, we're not going to do it. If you went through and used the standard or the general form of a quadratic equation, and you completed the square and you did all that work and you wrote it in standard form, in this form, then you would know that h is -b over 2a. Okay, that's not obvious, it's not something that we're going to do, but that's what it would be. So what we're saying is that if the minimum, if a is greater than 0, then the vertex is a minimum value. Then f of h is equal to k. So what we're saying again is that if a is greater than 0, so again it's pointing up, then the minimum value is at x equals -b over 2a, right? And then that function evaluated at -b over 2a is going to be h. But we're not going to do that. But I just wanted to show you that that's what's going on. So the most important part of this section are these first few questions, 9 through 24. I'll bring these in for the sake of completeness. Right, so we already talked about this one, and whoopsies, keep going to the wrong one. Not for long. So let me just make sure here. Good. If you completed the square and rewrote ax squared plus bx plus c in standard form, you would find h is equal to -b over 2a. That's all it's saying. Okay. Otherwise, it's the same thing in both of these. We're not going to do this, but I just wanted to kind of clarify. Okay. Any questions about this section before we move on? So a lot of work finding the standard form, but once you have it, it's pretty easy. Right? Well, I shouldn't say easy, but it's pretty reasonable. Okay, so for section 3.2, it's on polynomial functions and their graphs. We're gonna focus on just talking about polynomials, developing terminology around polynomials that we'll need. The graphs that we're gonna focus on are in 3.1 and 3.6. So this one, I'm just gonna kind of cover what we need, nothing that we don't. Polynomial functions and their graphs. Oops. Okay. For graphing, we will focus on 3.1, which is what we just did, right? Quadratics. And 3.6, which is on rational functions. Okay, for polynomials, like I said, we're just developing terminology mostly, general shapes, and then we'll move on to rational functions next day. Okay. So I posted polynomial functions part 2, which is for this week. If you have the notes that I posted last week, where I posted all of the chapter 3 notes together, I actually changed, or I shortened the notes for 3.6. So 3.6 now is only 1 page instead of 2. So if you have the old ones that I posted, then maybe just update them, that 3.6 one. Okay, so polynomial functions. Here. We've talked about polynomials before, so we know that it has a series of terms, right? So we've talked about the terms, we've got the coefficients, we've got degrees. So the highest power of x is the degree of the polynomial. And so all these a's out in front are called coefficients. And the last term is a constant term because it doesn't have an x. And so it's called a constant coefficient or a constant term. And a subscript n is called the leading coefficient. And the leading coefficient and the leading term here, it determines the overall shape or the end behavior of this graph. So that's what I want you to take away from this section here. So the leading term determines the overall shape and end behavior, determines the overall shape / end behavior of the graph of a polynomial, of the graph of a polynomial. Okay. So what does that mean? Well, depending on if, so here's our leading term, a subscript n x to the power of n. So we